So welcome. So this next section is on electrical potential, and this is the one that I keep playing with to try and get clearer, because there's a lot goes on in this section. There's new vocabulary, there's different situations, and I want to try and be as clear as I can about it. So let me give you a bit of an overview to begin with. So far we did the idea of the electric force. That was measured in newtons. And we said, well, okay, you have two charges, and one charge causes an electric field that the other charge sits in. So here's my big Q, and here's my electric field. And then I sit another charge in there, Q. So this other charge feels the effect, and say they're both positive, so there would be a FE resulting from it. You know, okay, the force electrical resulting from it. And then I said, well, supposing I want to know what this electric field is at this place, I don't need this charge there, I just need the actual position. And so I can talk in terms of the electric field line, which is E. So I can talk about an E. So E is to do with the point, and FE is to do with a charge at that point. So I have my electric field E, and that is in newtons per coulomb. And the gravitational analogy would be the force due to gravity, which is your weight, which is measured in newtons, and you would have little g, which you might have learned as 9.8 meters per second squared, which is a bit sad because then it's implying it's an acceleration. But it is actually a gravitational field strength, 9.8 newtons per kilogram. So, and we call it 10. Okay? Question or comment? Oh, sorry. No, it's all right. So that would be, G would be in newtons per kilogram in the gravitational thing. Okay. I can use analogies for this. So I use the analogy of, you know, when we did this thing on the class in the lab where we actually took two kind of like charges, and we imagined them as being like, one was a positive charge and the other one was a negative charge, and we thought of them as like contour lines, and we imagined boulders rolling down into these, you know, into the bucket, and these were lines of electric field, and these contour lines were lines of electric potential. So now where does this electric potential come from? Well, you may recall from mechanics, if you took a force and you moved it through a displacement, you got work, remember? And so what we said, and work is equal to the change in mechanical energy, basically, which is the change in gravitational potential energy if I don't allow any speeding up. Yeah? It's like we learned about the work kinetic energy theorem, but that was just to define kinetic energy. It's the work mechanical energy. When you do work, you change the mechanical energy. That mechanical energy can manifest itself in two ways. One way is gravitational potential. The other way is in kinetic. We can say only kinetic this time, only gravitational potential this time, or a bit of both. Well, let's say we have only gravitational potential energy. So we can say, well, delta U, my change in my work, is equal to delta U, my change in mechanical energy, and my change in gravitational potential energy. And that was equal to Fg times, I don't know, D or something, H or something, whatever you want. Yeah, remember that? Okay, so there's a link between a force and changing gravitational potential energy. So we need to talk about changing gravitational potential energy. So delta UG. And what we might talk about is on our mountain side, let's say we got our mountain side, the change in gravitational potential energy is the change in potential energy between there and there. That's my delta UG. Yeah, there's my delta UG. Going up or coming down, it's going to be a difference. Agreed? Okay. And that will be measured in joules, of course, yeah? And then we say, well, supposing that I want to know what the change in gravitational potential energy per kilogram is. Because, you know, you have more kilograms than me, so our two values are not going to be the same. But proportionally, it's interesting to know. So we define this thing called delta V, and this is delta VG, which would be in joules per kilogram. And this would be how many joules for every kilogram of you is changed in going from this height to that height. And I think it's really important. This is Fg. I think it's really important to get that gravitational analogy. I think this diagram is kind of like really useful because it kind of shows you, oh, we're in this gravitational field G, and we have a certain weight Fg, and then we were imagining going from, say, level A to level B. So there's a change in gravitational potential energy, and we've done all that. We did all that in mechanics. What's new is, and it'd be interesting to know the change in gravitational potential energy per kilogram of the thing that's moving. Not per kilogram of the planet, but per kilogram of the thing that's moving. And that would be the gravitational potential. So there's a little bit of an issue here. Yeah, this is gravitational potential energy, and this is gravitational potential. So it's kind of like you just missed off the energy and you got the wrong thing. All of this is useful for our electric field. So we can say, oh, we can define our change in electrical potential energy. And you'd get that by taking this electrical force and multiplying it by a distance. So we get delta UE, if you like, which equals Fe times some kind of distance measure, yeah? And that would be in joule, just the same. And then we have, let's take the number of joules, not per kilogram, but this would be per coulomb. And that would be in joules per coulomb. And that would be my change in electrical potential. And my analogy is, here's my electrical potential. I'm going from there to there. There's my delta UE. Here's my electric field E. Electric field E looks so important because it's a big capital E, and little g looks so unimportant because it's a little g, but they're both doing the same job. And then I have my, electric force. So that's the kind of game we play in this chapter. There's another wrinkle or two in there, but that's the kind of game we play in this chapter. Okay? 4 things in particular: electric force, electric field, change in electric potential energy, change in electric potential. Sometimes later on, I can talk about just not my change in electrical potential energy. I can talk about my electrical potential energy there at one point and my electrical potential energy there at another point. That's a little bit of a subtlety. And I could talk about my electric potential at that point and my electric potential at that point. But we'll get to that in a bit, okay? So we've been here before a bit, but we're going to have to recall all of that stuff we did in mechanics. Then we're going to add stuff to it. So it's a lot to do. So the first thing I think we need to do is just to make sure we have our definitions correct. And you know that I like analogies. So I'm making an analogy between Fg, the weight, and Fe, the electrostatic, or if you like, the electric force. I use both terms. I'm not sure which one's better. And then we have G, the gravitational field, and E, the electric field. And then we have delta UG, the change in gravitational potential energy, delta UE, the change in electrical potential energy, and delta VG, which we've never heard of before, but it's our change in gravitational potential, and our delta VE, change in electrical potential. That's your 9-volt battery has a potential difference between its 2 terminals of 9 volts. That's what that is. Okay. And in this, Q is like M. So they're kind of like equivalent to each other. Q is like M. Yeah. So these guys are all equivalent to each other. So we can kind of like visualize in one way and translate to the next. So the first thing I like to get down is your definitions, and I'm not above asking you for a definition. So we say gravitational force. Well, what did we used to say? It was the force experienced by one mass due to its position relative to another mass. Yeah, so that was measured in N, newtons. Gravitational field strength, little g, that was the gravitational force that a 1 kilogram mass would experience at that location. So if your second mass was not 95 kilograms, but was 1 kilogram, the numerical value equaled the gravitational field strength. It's important to recognize that you don't need that second mass to be there. The gravitational field is about the point in space. It's just numerically equal to the force you'd feel if you put a 1 kilogram mass there. And then we have change in gravitational potential energy, and we said that was the change in energy stored in a mass due to its change in position relative to the other masses. We move it relative to the Earth. We're doing work. We have a change in potential energy. We've been here before. And then the change in gravitational potential energy that a 1 kilogram mass would experience if it were moved between 2 points. And again, it's important to recognize you don't need the 1 kilogram mass to move. It's numerically equal to that value. The change in potential is between the 2 points. Change in potential energy is between a mass moving between the 2 points. Change in potential is between your mind going between the 2 points. And so we have newtons per kilogram, a newton meter, which is a joule, unfortunately, they name it after a person, and then newton meter per kilogram. Wouldn't it be nice if the units were that? Because you'd know to take a force and multiply it by a displacement and divide it by a mass. It would tell you how to do it, but we have joules per kilogram. And we did a lot of moving within a room. We had bags being lifted up, we had bags being moved to the side, and bags moving up a ramp. Remember all that? We didn't do so much of moving from near space to far space. We didn't do so much of that. These are new notes. I put them up last night, so you might not have them. So just they're up there now. You can download them afterwards, but just listen to what I'm saying, and it'll help. So we didn't do much about moving, significantly far away from Earth. But if I did, I would find that the electric field lines get further and further apart the further away I go. So the electric field strength gets less and less. So in this case, I have a uniform G. And in this case, I have a variable G. And we didn't do much of that in Physics 1. We kind of said if you go to the moon, G is 1.6 newtons per kilogram. And on Earth, it's 10 newtons per kilogram. Oh, look, it changed. We didn't do many problems where it changed. In electrostatics, we'll do a lot of problems where it changes. So that's the gravitational analogy. What about the electrostatic? It's the same thing. The force experienced by one charge due to its position relative to other charges. And then the electrostatic field strength is the electrostatic force that a 1 Coulomb positive charge would experience at that location. But remember, the field strength is about the point rather than the charge that's there. And the electrostatic potential energy, change in electrostatic potential energy is the change in energy that is stored in a charge due to its changing position relative to other charges. And then we say, well, the electrostatic potential, change in electrostatic potential is the change in electrostatic potential energy due to that a 1 Coulomb positive charge would experience if it moved between 2 points. And again, we have newtons, and now newtons per Coulomb. And we add Newton meters, which becomes a joule, and we have Newton meters per Coulomb, which becomes a joule per Coulomb, because we named the joule. And now we're going to name this. So this is the volt. So this is doubly hidden from you. Again, if it was left as Newton meters per Coulomb, you'd know what to do. You take something with force and multiply it by something with displacement and divide it by the charge. But maybe you might know which charge to use, but you'd know the charge should be divided. Whereas if I call it the volt, all that is hidden. So to some extent, you gotta get very comfortable with what a volt is, so it's not hidden from you so much. So really spend some time and get comfortable with those comparisons and know what those things are. Because if you don't, then frankly, all you're doing is recalling a magic formula, and you're trying to put numbers into this magic formula to get an answer. And it's not even clear that there's much understanding about what the answer means. You know, if you don't understand the definitions, then you don't really understand what the letters stand for, and so it devolves into some kind of like ritual where I give you some numbers that you put into something, and you get a number, and I check you off, and we all kind of go, oh, we understand that, but we don't really understand it. So really spend a bit of time and make sure you understand what these things stand for. To make things a little bit more interesting, in mechanics, we only dealt with uniform fields because we wanted to introduce this idea of work. We're doing a lot of things. We're introducing work and potential energy and changing potential energy, and we had enough on our plate, and now we've got that in our bag. The book assumes you kind of just did it yesterday, so you're very familiar with it, so you might want to go back and review some of that stuff. But now, because that's more familiar, we also, and because practical terms, we tend to have, in some areas, we have charges that are quite distant from each other. So we'll have uniform. You're joking. Sorry about that. I know nobody in Clinton, Maryland, so I don't know what that's about. So because of that, we have to deal in terms of non-uniform fields a lot more. So we're going to do both. How do we get a uniform field? Well, we could take a point charge and not move very far backwards and forwards like we do on the Earth. With the Earth, we have an Earth, and we don't move backwards and forwards very far in the room. And potentially it's uniform. Yeah, we take the two field lines, and they look pretty parallel to me on this scale. But as we go over larger scales of variance, from close to the charge to far away from the charge, just like as close to the Earth to far away from the Earth, we'd see that divergence take effect, so we get divergent fields. We also have in the electrical world, we have the ability to make a capacitor. And that's a whole array of positive charges on one metal plate, and a whole array of negative charge, that's a negative charge, on another plate. And as we found out, because we plotted in lab the other day, the field for this, the electric field lines were all nice and uniform, apart from the edges. And we had these potential field lines. So, and I think it's, again here, the gravity, it's just so ingrained in us that it's really useful. So how do I represent this two-dimensional electric field, electric voltage diagram to give me some gravitational insight? It's like having an embankment. So here's my first positive charge is high up. My negative electrode is lower down gravitationally. We have all these differences in height. So the voltage acts like a height. And my delta V is like a difference in height. So think of your voltage as being like a contour line value. 50 foot, 90 foot, 120 foot above zero, above sea level. And think of your delta V as being a change of 40 foot, a change of 70 foot. And then I can think of my electric field lines. And notice my electric field lines are nice and uniform and parallel to each other, so I have a uniform electric field. So there'll be times when I talk about behavior inside a capacitor, inside a uniform electric field. And that compares quite dramatically with non-uniform fields. And non-uniform fields, basically, I have my electric field lines diverging and converging at different points. So here, my electric field value would be quite small. And here, my electric field value would be quite big. Because here, the lines are close together, the red lines are close together, and here, the red lines are far apart. And these blue lines are my contour lines. They're like my height lines. They're the voltage lines. We call them equipotential in class. And they have a certain curvature to them. And, you know, they start and they end and go in circles and all that kind of stuff. All right, that's looking down from above as a map. If I want, I can draw me a 3D diagram of this where I basically have all these like boulders rolling down. We say the electric field is what a positive charge would do. So it's like a boulder rolling down from a mountain and going into a hole is like going from a positive charge to a negative charge. And they find the path of like, you know, easiest transfer. And so what we find is that the field lines are always at 90 degrees to the potential lines. That's interesting. Always, always, always. And they have circuitous paths, but they get there in the end. So can you see that the mathematics for this side here, the non-uniform, will be in principle the same, but in practice we're going to have to do a bit more fancy math. Because in this example, because over here in the uniform field, the electric field is constant. So it's going to have a value for a problem. Over here, the electric field is varying. So it's going to change as I walk along my path. The steepness of the slope is going to change as I walk along my path, because the electric field is changing. Do you see that analogy? So what we've got to do, and what I think the book does not do a very good job of, the book basically says I've got to derive these equations. I'm going to begin with the most general case, which is the non-uniform field. And then I'm going to simplify and get the uniform field. And it's almost like what I found was students could do some of the complicated problems, but they couldn't do the easy problems, the uniform problems, because by then they were like full up. You know, it's like, man, I'm done. And so they missed some easy stuff and they got some of the harder stuff. And what I'd like to do is reverse that a little bit and make it so that I think you can get the easy stuff and then you can focus more on the harder stuff. So that's my idea. I'm going to use the gravitational analogies all the time. If when you get the notes you don't like them, just cross them out. You don't need to worry about it, but it's there. So I thought we'd talk in terms of the gravitational force and the gravitational field and the change in potential energy and the change in potential. Because if you think about it, there's a relationship between these things. If I want to go from a force and figure out what the field is, rather than having a 6 kilogram mass and a 3 kilogram mass and working out what the force is, I pretend I've got a 6 kilogram mass and a 1 kilogram mass and figure out what the numerical value is, because it's the force per kilogram. Agreed? So, to go from the gravitational force to the gravitational field, I just divide by that little mass. Not the big mass, that's the big mass. I divide by the little mass, rather than get the answer and divide it by 3, in this case. Yeah? So to go from force to field, divide by the little mass. Change in gravitational potential energy is the gravitational potential energy of this guy, and the change in gravitational potential is the change in potential energy per unit mass. So divide by mass. So if I want to go from forces to fields, I divide by mass. If I want to go from change in potential energy to change in potential, I divide by mass. And frankly, if I want to just talk in terms of, if you recall, we kind of introduced this idea about just the actual value of the potential energy at a height. Not the change, but the value at height. And we can talk about the value of the gravitational potential. You're going to divide by m. So you want to go from the left-hand side of this diagram to the right-hand side, divide by m. You want to go the other way? I know the electric field, and now I'm putting a 3 kilogram mass in. I multiply by the little mass. So I'm going to multiply by m, multiply by m. And what's the equivalent for mass in electrostatics? What do we charge? Oh, so you want to go from electrostatic force to electrostatic field, divide by Q. You want to go from electric field to electric force, multiply by whatever Q you put in there. You want to go from change in electrostatic potential energy to change in electrostatic potential, divide by Q. You want to go from electrostatic potential, change in electrostatic potential to change in electrostatic potential energy, multiply by the little q. And again, we can introduce this idea about, well, sometimes we don't want to talk about a height difference. we want to just talk about the height. So we can talk about my electrostatic or electric potential energy at a point, and I can talk about my electrostatic or electric potential at that point. And again, if I want to go that way, I'm going to divide by Q. If I want to go that way, I'm going to multiply by Q. So we know how to go from forces to fields. We've known that for a while. We did that 2 chapters ago. And now, because of the definitions, we know we can do the same math to go from changing gravitational potential energy to changing gravitational potential. So we can just practice that a little bit. I did 4 examples, but we'll do. You guys have not got clickers, and I want to get a move on. So do you want to do me a favour? Can you just grab that and just pass the box around and just grab yourself a clicker? So a 15 kilogram mass, just pass it to the next person, and we can figure it out. A 15 kilogram mass weighs 45 newtons when it is located near a planet. So here's my planet. That's my big M. And a 15 kilogram mass, there's my little m. Weighs 45 newtons. That's going to be 45 newtons, and this is 15 kilograms. And what is the gravitational field strength? So I say, oh, my gravitational field strength, well, let's have a look. My Fg is equal to, well, what is it going to be? It's going to be m times g. Weight is equal to mg, remember that? And so my g is equal to Fg over m. So my g is equal to my Fg, which is 45, over my m, which is 15, which equals 3 newtons per kilogram. So there's my answer. Now, I did that kind of like the way that came into my head, but what I could have said was I have Fg and I have little g, and I want to find little g from Fg, so I'll go that way, and the way I do it is I divide by m, just from that diagram here, from the diagram on the left. I'm dividing by m. So this is a way of formalizing things, but I don't have to. I put a little box in the side so you can see where we're going. But that's the idea. Can you guys please do for me? Oh, rats! I wonder why that's not on. Let's have a look. I didn't click it. I'm sorry. I'm gonna lose this. Discard. Let's have a look. Hiding from me. Just single click on it. Come on, old friend, you can do it. I'm going to do that. Let's have a look. It's going to be somewhere else, isn't it? Let's go there. Let's go all programs. Where are you? Do I care this much? Probably don't. There it is. iClicker win. iClicker. iClicker's already running. So where is my little?
You can close the one that's open in the bottom and restart it.
Is there one open here? Oh, there is. That's what I want. Thank you. So I need to get out of here. So I need to get out of here. Minimize. it's going to minimize. No, that's not it. It's not that. Close this window. Thank you. You're right. I'm trainable. I'm just not. Oh, this has all been recorded. So let's have a go at the bottom one, and I'll pause through it. So let me do this one because the answer's not there. So let me go here, and that might happen on a few of them because I was trying to rush through a little bit. So we say a 60 coulomb charge experiences. So here's my little q, and that's 60 coulombs. And it experienced electrostatic attraction. So here's my 12 newtons. And here's my big charge, q. And what I realize, of course, is that if I want to go from a force to a field, I've got to divide by little q. So I can say, well, my force was 12 newtons divided by my q, which is divided by 60, which is going to be 1/5, which is 0.2 newtons per coulomb. To put that down more in equation form, I would say Fe is equal to Q times E. So E is equal to Fe over Q, which equals going to be 12 over 60, which equals 0.2 newtons per coulomb. And I must confess I prefer recalling the equation. The little box helps me if I'm stuck, but I still want to use my equations. Yeah. This was some more practice. I'm going to leave it because I probably also got mistakes in that as well. Okay. So let me stop that because we don't need it. Okay. Now let's worry about the up and down bits. And the up and down bits, let's just think about forces and energy, gravitational potential energy. We did it by multiplying by the displacement and etc. Yeah. We said work is equal to my change in my gravitational potential energy, which equals the force times the displacement. Yeah. And when they're all in line with each other, then everything's great. I've got to worry about the sign. Is the force up and the displacement up, in which case it's positive? Is the force up and the displacement down, in which case it's negative, and all that kind of stuff? Yeah. But that's how I do it. And of course I can remember that was equal to m times g, so I can even bring electric gravitational field in here without even realizing it probably when we first did it. We didn't really think mg, oh, that's the mass times the gravitational field, but that's what it was. We just learned that's how you do it, So, okay, that's in principle all we're doing. We're just going to, if we want to go from the force to the change in gravitational potential energy, we multiply by the displacement. And we did this little wrinkle thing where you probably learned that PE is equal to mgh. How many people learned that? Yeah, and you were kind of like, again, it's kind of like it's very convenient at that time to talk about it like that, but it raises a whole bunch of problems because that h is not from the center of the universe. So we're really talking about that height's been a change in position, which means that is really a change in potential energy. When we said that the potential energy of this block on the top of the table was 7 joules, it was relative to the floor. So it was a change in potential energy relative to the center of the universe. I have no idea what the potential energy at the top of the table is relative to the center of the universe. So we ended up with this complicated thing about, well, we don't know where the center of the universe is, so we'll take the outside of the universe and work our way downwards. And we end up with this really uncomfortable thing that the potential energy at this point is a negative value. That's even more negative, but that's a negative value because we know that's 0. If I don't know where the bottom is, I surely know where the top is. It's just significantly far away from any attractive mass. So call that 0. It's like I took my number line, and rather than trying to measure from some bottom up, I measured from top down. And rather than having this be 0 and this all be positive, so going upwards is a positive change, I have this be 0 and these all be negative, so going upwards is a positive change. So in both cases, a positive change. So it works. We're just moving our ruler. And it's just comes so fast, and it's confusing, but just spend a bit of time and just get more comfortable with it. You do the same thing in chemistry with electrical potentials for atoms, energy levels. You do the same thing in that as well. When you don't know where the bottom is, go to the top and start counting downwards. Works. All right. So, okay. In principle, this is a piece of cake. There's 3 possibilities. One is that we move along a field line. So we're uniform, and we're moving along a field line. And for that, all you do is multiply the force by the displacement along the field line. No big deal. If you want to go from electrostatic field to electrostatic potential, change electrostatic potential, do the same thing. Yeah? I want to just cut to the explanation. Okay? Then the next complication was, oh man, this is similar, except we're not moving along the field line, we're moving through field lines, we're moving maybe a bit sideways, maybe, So we said, oh, well, it's still that force times that displacement. The only thing is we weren't given that displacement, we're given that displacement, we're given that angle. So we said, oh, that's no big deal. I know that this is, the work is equal to the force times my delta x, which equals my force, times d times the cosine of the angle between. Agreed? Just using trig. D delta x is d cosine theta. Just using trig. And then you said, oh, well, if I make these two both vectors, I can use a dot product. Remember using the dot product in physics 1? No? Well, you got to go back and remember it. So dot product. So it's basically we have f dotted with d, and f dotted with d is the magnitude of f times the magnitude of d times the cosine of the angle between. Okay? So, great. So that tells us, for instance, if I move sideways, because my angle is 90, cosine of 90 equals 0, there's no change in potential energy when I move sideways across electric field lines. Oh, that's an equipotential line. There is no change in potential energy. There's no change in potential. It's an equipotential line. So you see where that comes from. So rather than saying that, oh, my change in potential, before we said my change in potential equals the force times the displacement. Now I'm saying my change in potential equals my vector force dotted with my vector displacement. Agreed? Yeah. And the same thing goes for the, changing from the field to the electrical potential, to change electrical potential. Can do electrostatically. I'm just going to say, oh, in that case then it's going to be my work is equal to my change in electrical potential energy, which equals my vector electrical force dotted with my displacement. Just the same. If I remember that my electrical force is equal to the charge times my electrical field, I even get that next little wrinkle. Yeah? But now we get a little bit more complicated, because now we're dealing with non-uniform fields. And the answer is, well, I'm moving across field lines, but the field lines are diverging or converging or something. So what I've got to do is break this journey up into a whole lot of little steps. And for each little step, I've got to take a little bit of displacement, and there's a little bit of field change. The field's getting a little bit different with each step, and it's getting a little bit of displacement, and a different angle between them. So this is a real pain. So if you think about it being, you know, work is equal to delta UG, which equals, it's going to be the sum of each little bit of that force dotted with each little bit of that ds. And I do enough of those, I get the integrals, you know, the integrals of these things. And of course, I can change from the force to the mass times the gravitational field and take the m outside, because the mass doesn't change. It's just a little g that changes. Yeah. So we get this, where we say, oh, the gravitational, changing gravitational potential energy for, this should be electrical. I got all my letters right apart from that one, I think. Is going to equal the electrostatic force dotted with the ds integrate. So we did the force times the distance. We did the force dotted with the displacement. Then it was non-uniform. We did the integral of the little bit of force dotted with a little bit of displacement. Doesn't that kind of like conceptually just follow naturally? It's like you're just getting a bit more complicated diagram, so you have a bit more complicated math. But, you know, you have to take into account the direction when you're not going down the field line, okay? And when you're curving around in a curving, changing field, you've got to break up into little bits of journey and add up all those little bits of journey. You can't just do one entire thing. You've got to take little bits. Does that make sense? Okay. So, with that underpinning, I'm going to actually go back to the notes that you have, which are also in the book, which are basically how they use these things. And we'll talk a little bit about that. Some of it we won't need, but I think with that you might be able to see where some of this stuff comes from. The book prefers to talk in terms of electrical change in potential. The book just prefers to jump in with electrical potential. And I just think, okay, I'll go with it. But because you can measure potential lines. You did potential lines. So you're kind of been introduced to it. But what we say is if the electric field is uniform, consider a uniform field in the y direction. So there's my y direction. I'm going from A to B, and the separation is D. And we say, because the direction is, so they give the general form. We said delta U is equal to the integral of Fe dotted with ds. And what they're saying then, well, if we divide both sides by Q, we get delta V is equal to the integral of E dot ds. That's where that comes from. And they prefer to approach it from that point of view, because you're familiar with and you can measure potentials. You can't measure so easily potential energies. Okay, so we get the negative sign is because you tend to roll down hills. And that's just to get the sign right. We have positives and negatives, so a positive charge, let it go, it's going to decrease in its potential. If you think back, that diagram's a long way back. If you think about a positive charge on this bottom diagram at the right, you're rolling downhill. When a positive charge goes with the electric field, it's got less and less potential. Yeah? So the change is going to be negative. When a positive charge is rolling, is following the electric field, it's going to be a negative change in potential because you're rolling downhill. Okay. So we have a negative sign. So it's basically a negative sign. We're going from A to B, E dot ds, and we say, well, hold on, let's expand this. So it's the magnitude of E times the magnitude of ds times the cosine of the angle between them. But the cosine is the cosine of 0 because there's no angle between them. ds is in the same, my ds, if you like, my ds is in the same direction as my field line. So that's cosine of 0, which is 1. So that equals 1, so it goes away. So I get the integral minus the integral of E times ds E's a constant in this, isn't it? It's a uniform field, so E's a constant, so take it out of the integral. And so we have this ds is this little bit. Sum up all those little bits, integrate all those little bits, we get the distance, which is minus E times D. Isn't that what we started off with? We said we take our force and we multiply it by the displacement, or we take our field and we multiply it by displacement to get our potential. So mathematically, this is justifying what we kind of saw intuitively by analogy from our gravitational work. But it's still true. So there's an equation to put away somewhere. Delta V is equal to minus ED, but uniform.
Has to be uniform for.
Has to be uniform because you got rid of that cosine theta because they were parallel. Okay?
So the way for us to know the uniform in the problem you said is uniform. For
Oh, I'll draw parallel lines. I can just draw parallel lines. Or I can say it's a capacitor. I mean, there's lots of ways I can say it's uniform. But, you know. The change in potential per unit charge is the force per unit charge times the displacement that the force moves through. Okay. Okay. This makes sense. Well, it does. With the you're getting a lot of things thrown at you at once. It does make sense. Everything we say makes sense. Note the electric field lines point in the direction of low potential. Change in potential energy. Well, the change in potential energy is just Q. I'm calling this Q naught now. Q naught times delta V. So it's delta U equals QED. So delta U equals minus QED. Quite easily done. And I remember learning that when I first started doing this stuff. Quite easily done. So we have delta V is equal to minus ED. And delta U is equal to minus QED. Do you need to learn both of them? I'm not sure you do. If you know that relationship, then you only need to know one of these equations. If you know that, the way I get from delta U to delta V is I divide by Q, then take your equation for delta U and divide by Q. So I'm not learning two equations there. I already know some relationships. I'm not going to learn every equation possible. The book gives you every equation that's possible. I wonder why sometimes. It just makes it so much harder. So QED. But that, I think QED, delta U equals QED, really important equation. Let's say you are not moving in the direction of your electric field. Well, we still want that displacement. That's the displacement we want. But we've been given this other vector. So we say, well, my change in potential is equal to minus the integral of E dot ds, where ds is this little bit. I'm going to integrate all these little bits of ds. They all happen to be in a straight line. It's the summation of all these little bits of ds. And let's have a look. E is constant still. They're not in the same line as each other, but E is constant. So this would be E dotted with the integral of ds. And let's have a look. Oh, yeah, the integral of ds is just big S, little vector. So that's minus E dot times S. And I can say this is going to be E times S times the cosine of the angle between, etc., etc. Yep. Let's say we decide to go at 90 degrees. So we're going from there to there. Then this is going to be the same, except that this cosine theta equals 0, because it's 90. We knew that conceptually before. So mathematically, we're just using this thing. Look, it works. It looks in this case, it works in this case, it works in this case, it works in this case. And I see what the book is doing. It's using the analysis for the most complicated thing. and showing it works for the simple things. That's it's kind of confidence building. Look, this works. Look, this works. Look, this works. But to my mind, it's kind of like it's making the easy stuff kind of a lot harder because it's throwing away all you learned about mechanics or making it less obscure, more obscure. Consider a parallel capacitor that is used to create a uniform electric field, 6 newtons per coulomb. So I know my E. What is the potential difference between point A and point B? So let's have a look. I want to find my potential difference, delta V, and that equals, I don't know, and my E is what I know. That is going to be 6 newtons per coulomb, and my displacement R, my delta X if you like, is equal to 5 minus 2, I'm sorry, minus, let's just ask for what is the potential difference. I'll sort the sign out afterwards. It's 5 minus 2, which equals 3 meters. Scratch, scratch, scratch. I know that delta U is equal to the force times the displacement times the cosine of the angle between. And I know that delta V is I know that delta U is equal to Q times E times D cosine theta. And let's have a look. I know that delta V is equal to delta U over Q. So delta V is going to equal Q times E times D cosine theta over Q. Delta V is equal to, oh my word, what was that? E times D cosine theta. So in this case it would be, so taking this up here, I say delta V is equal to E, which is 6, times D, which is 3, times the cosine of, let's just draw a D on there, cosine of 0, which equals 1. So delta V is equal to 18. And now let's think about our sine. We're going from high down to low, so our potential energy will be decreasing. So our potential, if we think about it, there's the positive. We're going from the positive to the negative. There's my delta V. It's the changing kinetic energy, changing potential energy per unit charge. And I'm going definitely in a negative direction, aren't I? I'm going from A to B. So that should be a negative value. I tend to look at my signs afterwards when I look at my diagram. Some people are real sticklers and they kind of like want to get the signs right all the way through. I suppose I should be. I'm not so good at that, but that's the way I go. Very often in tests I will say, if you look at old tests, I'll say what's the magnitude, because I realize that for some people that's an issue. Sometimes I test you on it, sometimes I don't. Cool? So we could have just also said that delta V is equal minus the integral V dot, what was it, ds, and that would have given us the same answer, you know. I don't know. There's so many ways of solving these problems. Some look easy, some look hard. They're all easy with practice. They're all hard without, you know. So, how much time do I have? I have 6 minutes. Consider a parallel plate capacitor that is used to create a uniform electric field of 11 newtons. So I gave you the E. What is the potential difference? So I'm going to say delta V is equal to, oh man, I got a delta U is equal to, what did we say? I'm rushing. I can feel myself rushing. It's never good to rush. So delta U is equal to F times D times the cosine of the angle between. Delta V is equal to E times D times the cosine of the angle between. I look at my diagram, I know E is equal to 11 newtons per coulomb. I know that my D is equal to, I'm just looking at that, that's 4 meters. So I know my delta V is equal to 11 times 4. And this is, oh, man. Oh, I see. I'm sorry, no. I did a little bit in my head that I shouldn't have done. So which distance do you use? Do you use that vertical distance that's in line with the electric field? Do you use the horizontal distance, which is perpendicular to the electric field? Or do you use the path actually taken? And what you do is you use the displacement in line with the electric field. Yeah? If you use the displacement, you use the cosine of this angle, which gives you the displacement in line with the field. So I kind of cheated. This delta, that D is parallel to E. The D parallel to E is 4 meters, which equals 44 volts. And now I look and say, oh, look, I'm going downhill, so that's going to be a minus 44 volts. Agreed? Cool. In this case, have I got time? Maybe. In this case, it says, consider a parallel plate capacitor that is used to create a uniform electric field of 9 coulombs. So E is equal to 9 newtons per coulomb. What is the change in potential energy experienced by a 4 coulomb charge? So I have delta U is equal to, I don't know, but I know that little q is equal to 4 coulombs. Positive charge, move from point B to point A, point B to point A. Oh man, I'm throwing a lot of things at myself here. So, and my D parallel to E is equal to 3 meters. And I say, well, my delta U is equal to F delta X when they're parallel to each other. And they are parallel to each other, so I'll simply take it like this. And I say my delta U is equal to Q times E, because I know that that's what my F is, times delta X. So my delta U is equal to my Q, which is 4, times my E, which is 9, times my D parallel to E, which is 3, which gives me 4 9s 36, and 3 36s is I think 108. And then I go work out the sine, and I am going uphill. Yeah, I'm going uphill. The E is pointing downhill. I'm going uphill. So I expect a bigger positive. So it's got positive joules. What is the change in my potential energy? I'm going uphill. So it's a positive change in potential energy. So it is A rather than D. And I'm going to stop there.